Hi folks, today we're going to be talking about something called biconditional statements. We're also going to talk a little bit about definitions, not the definitions of things, but just definitions in general and how you can rewrite them. So if you open up Kami, you're going to notice that you just have a blank page. You need to scroll down to find the notes. So there was an extra blank page inserted. And so if you scroll down, there's the notes. So today we're talking about biconditional. Biconditional statements are statements that can be written in the form P if and only if Q. So P if and only if Q. So in the past, conditional statements are written as if P then Q. So these biconditional statements are written as P if and only if Q. And what this means is if P then Q. And it also means if Q then P. So we have exchanged the hypothesis and the conclusion. And so not only do we have if P then Q, we also have if Q then P. That's what the biconditional means. It means it goes both ways. So if you write this symbolically, then you're going to have a P and then an arrow pointing both directions and then a Q. So this means that not only does P imply Q, but Q also implies P. And this should look familiar to you. The P implies Q, that's the conditional. But if you exchange the P and the Q to get if Q then P, that is the converse. So here we have that the conditional and the converse kind of go together to create a biconditional statement. And the way that you write it is hypothesis, if and only if, conclusion. Now, sometimes in your writing, if and only if is shortened. It's abbreviated. And it looks like this. It's if and only if. So it's like a double F if. Which sounds like it would be kind of fun to say 5 times fast. But if and only if is sometimes shortened to IFF. And that way we kind of understand that it's being implied that the hypothesis implies the conclusion and the conclusion implies the hypothesis. The converse and the conditional, the converse, and the conditional are together. I also want to point out that this here printed looks different than if you write it. So a lot of times you will see this. So even though the arrow that's printed just has like 1 bar in here, you sometimes also see like a double bar arrow going on with pointing in both directions. So if you see that, don't be freaked out. It means the same thing as just this biconditional symbolic representation. So I'm going to scroll down to example 1. And in example 1, it says, determine the conditional statement and converse within each biconditional. So it gives us a biconditional statement, and it wants us to extract or pull out the conditional and the converse. So example 1A, and I'm going to do the same thing that I did yesterday. I'm going to underline what I think is the hypothesis. I'm going to circle what I think is the conclusion, and that's going to help me kind of keep my statements straight in my mind. So example 1A says, 2 angles are congruent if and only if, there's that biconditional language happening here. 2 angles are congruent if and only if their measures are equal. So my hypothesis is that 2 angles are congruent. My conclusion is that their measures are equal. And something else that I want to point out is the subject of the biconditional statement is two angles. Okay, two angles. That means that the subject, regardless of writing the hypothesis or the conclusion first, the subject is two angles and it needs to go at the beginning of your statement, because you can't have a sentence without the subject. You can't refer to the subject at the beginning and then not mention what it is until the end. So in a conditional statement, that's if P, then Q. So if two angles are congruent, and I'm going to use the congruent symbol just for abbreviation. If two angles are congruent, then conclusion, their measures are equal. So think about it. If two angles are congruent, does that mean that their measures are equal? Why, yes, that's exactly what that means. So I would like to make sure that we label this as true. So let's go ahead and write the converse. Remember that the converse happens when you exchange the hypothesis and the conclusion. Converse is a brand of shoe, and if you don't like it, then you go to the store and you exchange it. So I'm going to exchange the P and the Q. Remember that I want to start my statement out with the subject. So if two angles, probably help if I write it correctly, huh? If two angles, and what's the conclusion? The conclusion is their measures are equal. So if two angles have equal measures, then hypothesis, they are congruent. So think about it. Is that true? If two angles have equal measures, does that mean that they are congruent? Absolutely. It sure does. So the conditional and the converse are both true. That means that our biconditional statement up here is also true. So I'm going to scroll down to example 1, should be 1B, but it's not, it's 1C. Why not, huh? This example, I would like for you to pause your video and try to figure out the hypothesis, the conclusion, and rewrite the conditional and converse from that biconditional that's given. You can use the previous example as a guide, but pause your video and check back for the answer. So our subject is Jennifer. The hypothesis is Jennifer is a member. If and only if is the connecting statement that shows this is a biconditional statement, and she has paid the $5 dues is the conclusion. So the conditional statement, if P then Q, is if Jennifer is a member, then she has paid the $5 dues. So if you think about that, if somebody is a member, they probably have paid the dues, right? So this should be a true statement. The converse, where I exchange the hypothesis and conclusion, is if the subject, Jennifer, paid the $5 dues, then she is a member. So if you pay your dues, typically you become a member. So this should also be true, meaning that our biconditional is true. So hopefully that went all right for you. I'm going to scroll down to example 2. Example 2 says, for each conditional statement, write the converse and a biconditional statement. So this time we're given a conditional statement. We need to write the converse, so we need to write if Q then P, and we need to write the biconditional statement using if and only if. So now you actually get to practice writing that biconditional statement. So in part A, it says if 2x plus 5 equals 11, then x equals 3. So these are very simple mathematical hypotheses and conclusions. So this hypothesis is 2x plus 5 equals 11. The conclusion is x equals 3. This is P implying Q. Looks like A, but it's a Q, sorry. The converse, where I exchange the hypothesis and the conclusion, is if x equals 3, then 2x plus 5 equals 11, period. Let's check that. If x equals 3, is it true that 2x plus 5 equals 11? If I substitute 3 for x, 2 times 3 is 6, 6 plus 5 is 11. Is this true? You bet, it's true. Is it also true that P implies Q? So if 2x plus 5 equals 11, then x equals 3? Well, let's solve it. If I subtract 5 from both sides, I'll have 2x equals 6. And if I divide by 2, I get x equals 3. So yes, this is true as well. Which means that my biconditional must also be true. And when I write it, it's that P, if and only if, Q. So I have my hypothesis, 2x plus 5 equals 11, if and only if x equals 3. Ta-da! All right, let's try the next one. The next one, remember, is a conditional. It says if a point is a midpoint, then it divides the segment into 2 congruent segments. So I've got my hypothesis, and it's implying my conclusion. So my converse, where I exchange the two, is if, what's the subject? It's not it. The subject is a point, right? That's the it that we're discussing in this conditional statement. So if a point, where's my conclusion? It's over here. If a point divides the segment into 2 congruent segments, running out of space, sorry, then the hypothesis, it is a midpoint. There we go. So let's think about if this is true or not. If a point divides the segment into 2 congruent segments, then it is a midpoint. Well, by definition, a midpoint is a point, and it divides the segment into 2 congruent segments. So yes, this converse is true. If a point is a midpoint, then it divides the segment into 2 congruent segments. Yes, this conditional is also true, which means my biconditional will be true. And if I write it, I start out with my subject and my hypothesis. A point is a midpoint. If and only if, my conclusion. It divides the segment into 2 congruent segments. Okay. So for a biconditional statement to be true, both the conditional and its converse must be true. If either the conditional or the converse is false, then it's kind of like a counterexample in the sense that it blows it for everything. If either the conditional or the converse is false, then the whole biconditional statement is also false. It can't be true. So let's look at example 3. Example 3 says, determine if each biconditional is true. So determine if it's true, and if it's false, you need to give a counterexample. I'm sorry, I realize underlining the entire question does absolutely nothing, so please don't underline the whole question like I did. So A, example 3A, says that an angle is a right angle if and only if its measure is 90 degrees. So remember that in order for a biconditional statement to be true, you have to check that the conditional is true and the converse. So in example 3A, is it true that if an angle is a right angle, then its measure is 90 degrees? Yes. Is it true that if an angle has a measure of 90 degrees, then it's a right angle? Yes. So if both the conditional and the converse are true, then this biconditional is also true. Let's look at part B. Part B says y equals -5 if and only if y squared equals 25. Now this one is a little bit harder to imagine because it's an equation. So if y equals -5, then y squared equals 25. Is that true? If y equals -5, then if you square it, do you get 25? Yeah, you sure do. Let's check the converse. If y squared equals 25, then y equals -5. Is that true? Not necessarily. That is not necessarily true. The converse is false, so the biconditional is false. What's the counterexample? If y squared equals 25, then what's another value that y could have? Y equals +5 is the counterexample. So at this point, we've practiced more with the conditional and the converse. We know about the biconditional. We know what it is. We know the words to look for in a sentence, if and only if. We know to abbreviate it, it's IFF, and symbolically, it's an arrow pointing in both directions. We know that a biconditional is only true if its conditional and converse are true. And if it's false, then we've got to provide a counterexample to prove that it's false. So we've learned quite a bit in this lesson already. Now I want to shift thinking to definitions. Now this is not a totally different topic, but it is a slight shift in our thinking from the notes today. So a definition that describes a mathematical object can be written as a true biconditional. A good definition can be used conditionally and conversely. For example, if a figure is a quadrilateral, then it is a four-sided polygon. If a figure is a four-sided polygon, then it is a quadrilateral. To make sure a definition is precise, it helps to write it as a biconditional statement. So let's check these definitions that were given about mathematical objects. We need to write each definition as a biconditional, and we're given three definitions, one of a triangle, one of a quadrilateral, and one that talks about the measure of a straight angle. So A says a triangle is a three-sided polygon. Well, a triangle is a type of figure, so that's going to be my subject. and I need to write it as a biconditional. So my biconditional is going to be hypothesis, if and only if, conclusion. So a figure is a triangle, if and only if, what? What is the conclusion? Well, the conclusion is that it is a three-sided polygon. A figure is a triangle if and only if it is a three-sided polygon. So it makes sense because if I check the conditional and the converse, they should both be true. If a figure is a triangle, it is a three-sided polygon. And if a figure is a three-sided polygon, then it must also be a triangle. So that definition of a triangle works very well and is precise because you can write it as a biconditional statement. So I'd like for you to try part B, pause the video, and write your definition as a biconditional statement. Part B as a biconditional should be rewritten: a figure is a quadrilateral if and only if it is a four-sided polygon. You may start using the abbreviation of if and only if with IFF if you choose to. And then finally, the measure of a straight angle is 180 degrees. The subject is a figure, so the straight angle is a figure. A figure is a straight angle. What follows to make it a biconditional? A figure is a straight angle if and only if its measure is what? If its measure is 180 degrees. It's a good, precise definition because it can be written as a biconditional.